In the last video, we learned how to calculate the acting error of a feedback loop when the inputs to the loop are steps, ramps, or parabolas. We saw that those errors might be 0, infinity, or a finite number, depending on the number of integrators within the loop. Now, if you have a look at any basic control book, you will find a table relating each type of system with the errors appearing for each of the standard inputs. And they talk about position error, velocity error, and acceleration error. Well, those are simply the errors we calculated in the last video. That is, the errors for step, ramp, and parabola. So the position error, EP, the position error, is just the error in the steady state for a step input. That is when R of s is equal to 1 over s. The velocity error, EV, is just the steady state error when the input is a ramp, or in other words, when R of s is 1 over s squared. And the acceleration error is, well, the steady state error for a parabolic input, parabola, or in other words, when R of s is equal to 1 over s cubed. So position, velocity, and acceleration. These terms come from the application of automatic control to actual position control systems, mechanical systems in which the objective is to control the position of some element. These kinds of systems are often referred to as servo mechanisms. And in them the association between for example a constantly changing desired position, the reference, and the idea of velocity is clear. But in general systems, the ideas of position, velocity, and acceleration may make little sense. So the only thing you need to keep in mind is that position is associated with step input, velocity is associated with ramp input, and acceleration is associated with the parabolic input. So as I was saying, most books come with a table including all the results we arrived to in the last video. It's something like this: EP, EA, no, EV, and EA. And here type 0, type 1, and type 2. Well, I'm not very fond of this stuff because it makes the students try to remember more things than they really need to. But anyway, I guess it pays to have a look at it, at least not to be daunted when you see it on the books. So according to our results, this is 1 over 1 plus the limit when s tends to 0 of all of s. And this for type 1, this is 0, and this is 0. Type 1 and type 2 systems have 0 position error. But type 0 systems with no integrators have infinity a velocity error. They have an error of 1 over the limit when s tends to 0 of s all of s, and 0 and type 2 systems have 0 velocity error. And finally, this is infinity, and this is 1 over the limit when s tends to 0 of s squared all of s. Okay, well, in the books they also defined this term here as kp, capital Kp, or the position error constant. This is denoted as capital Kv, or velocity error constant or coefficient, velocity error coefficient. And this here, this one here, is often called Ka, or acceleration error coefficient. Well, obviously in these other cases, Kp is equal to infinity, here Kp is equal to infinity, here Kv is equal to infinity, this one Kv is equal to 0, and here Ka is equal to 0, and Ka is equal to 0. Okay, again, I don't see the point in defining them, well, apart from making students' life miserable. Even more so when, as we saw, in all cases in which they are not 0 or infinity, this is just k, the k of the open loop transfer function, that the isolated gain, this k here in all the cases in the diagonal. So I don't know why they define them, but well, just keep in mind that they exist. So again, as I said, you don't need to learn this by heart, as long as you're capable of calculating the Laplace transform E of s of the error signal, and then to apply the final value theorem, to it, you'll be capable of understanding any kind of steady state specification, because they will give us specifications concerning the steady state errors, and you will be able to deduce, one, the minimum gain that you need to fulfill the specification, and second, the number of integrators, if any, number of integrators that you need to, again, to fulfill the specification. This is the most important part of the analysis of errors in the steady state. Well, another reason why I don't like this table is that it might be okay for simple unity feedback systems. Let me draw one here. Here it is. So the table may be okay for this system, this kind of systems, but for systems with non-unity feedback, or in series with other systems, or even part of more complex systems, the table may be deceptive. It depends on how we define AP, AV, and EP, EV, and EA. If they refer to the acting error EA of S, and the input to the loop, then the table is okay and it is valid in all cases. But if we are interested in the actual error between the overall reference, and the overall output, well, in general, the table is not giving us the information we want. So in my opinion, if you don't try to remember the formulas of the table, but you deduce them whenever you need them, you'll be less likely to be fooled by non-unity feedback or even more complex systems. Because in each situation, you will think, okay, what are they asking me for? On what signal should I apply the final value theorem? Is the acting error the same as the actual error in my system? What will I achieve if I raise the loop's type? Should I introduce some extra element out of the loop to achieve good tracking? Okay, I hope you're not more confused now than at the beginning. If you are, let me know.